In this section, you'll learn about the OSI reference model. The OSI model is a conceptual framework that helps lay out how computer networking protocols should work with each other. And it really helps aid your understanding as you're learning about networking as well. Actually, this is going to form the bedrock of your understanding of networking, so it's a really important section. We'll also go into the definitions of the different layers that make up the OSI model before covering them in much more detail in later sections throughout the course. We'll also cover the TCP/IP suite and discuss how it relates to the different layers of the OSI model. In this lesson, I'm going to give you a very basic introduction to networking. If you already know about switches and routers and network topology, you can just skip right on ahead to the next lesson. But if you're brand new to networking, then I'm going to give you a quick overview here. So let's say that we've got an office which is in New York for our company. In that office, I'm going to have end hosts like PCs, a server, and a printer, like you can see here, and they're going to need to be able to communicate with each other. So for that, I'm going to put in a network switch, and I'm going to cable my devices to that switch with Ethernet cables. And that's what a switch looks like. There's a Cisco switch. You can see it's got a lot of ports in there so that I'm going to be able to connect in a lot of devices. The switch is what allows connectivity on my local area network. In that office in New York, maybe I've also got a laptop, which is going to connect in over a wireless network. So for that, I'm also going to have a wireless access point, which is also going to connect into our switch. And that's what a wireless access point looks like. So I've got all my devices in New York now. They can all talk to each other. I've built a local area network. A local area network is a network that connects devices which are in the same local area, like in a single office or maybe a university campus. Okay, I don't just want my end hosts in my office to be able to talk to each other. They're going to want to communicate with other devices out on the internet as well. So for connectivity out there, I'm going to need a bit more of an advanced device, which is a router. A router is able to make advanced routing decisions to route traffic between different areas of your network. That's why it's called a router. And this is what a router looks like. You can see it's pretty similar to a switch, same kind of size. Typically, it will have less physical ports on there, and it will support different types of ports so that it can connect different types of networks as well. Next thing, we know that there's going to be bad guys out on the internet, hackers who are going to try to attack us, so we need to guard against that, so we're going to put a firewall in place. And this is what a firewall looks like. Again, you'll see that our different network devices tend to look very similar to each other, but they fulfill different tasks on the network. The firewall secures the different parts of our network from each other. Okay, so that was our New York office, the local area network, and its connectivity out to the internet. In a larger company, we're not going to just have one office in New York. In our example here, let's say we've also got an office in Boston as well. In Boston, we're going to have a similar kind of setup, the same kind of devices in there. We're going to have the local area network in Boston, and we've also got local connectivity to the internet from Boston as well. Now, because we're the same company, I'm going to want to have connectivity between my New York and my Boston offices. I want the end hosts in both of those sites to be able to communicate with each other. It is possible that they could communicate securely over the internet if I set that up, but another way of doing it is I could maybe put in a dedicated connection between my two routers in both sites, and that's going to give me my wide area network connection between my different offices. Okay, so that's a really quick overview of networking. And the point of networking is to allow that connectivity between our different end hosts on the network. So looking now at the characteristics of a network, we've got the topology. If I just go back to that previous slide, this is an example of a network topology diagram. The topology is how the devices are connected up to each other. Other characteristics is the speed of the network. Typically, the faster the network is, the more it's going to cost you, and cost is itself a characteristic as well. Things that will affect the cost are the type of devices you have in there, the size of the network, the different technologies you're using, etc. Other characteristics are security. I mentioned the firewall in the previous slide. We're not going to just have security on our firewall though. We'll also have security features on our routers and on our switches, and we can have other security devices such as intrusion prevention systems as well. Next, we have availability. We're going to want to make sure that our network always stays up. And for mission critical components in the network, typically we don't want any single points of failure, so we will double up on those components so that if any one fails, we've got an alternative component that will still be up and running. Scalability is also important. We want to design the network in such a way that it's easy for it to grow with our company without requiring a redesign. And reliability, similar to availability, where we want to make sure, again, that the network is going to be reliable, but it's going to continue to work. In this lesson, you'll learn about the OSI model. The Open Systems Interconnect model is a standard of the International Organization for Standardization. So it's an ISO standard. It's a general purpose framework that characterizes and standardizes how computers communicate with one another over a network. So the OSI model, it's conceptual. It's not a physical thing or an actual protocol or technology. Its 7-layer approach to data transmission divides the operations into specific related groups of actions at each individual layer. And a layer serves the layer above it and is served by the layer below it. Now, I know that doesn't make much sense yet, so let's have a look at how this works in action. So let's look at an example. Here I've got a sender on the left. Let's say that's my laptop. And we've got a receiver on the right. Let's say that's my email server, and we're both connected into a switch. And I'm going to send an email to my email server. So obviously the sender is going to compose this traffic that's going to be sent to the receiver. And as it builds this packet that is going to be sent, it's going to start off at the top level and then it's going to work its way down to the bottom level. So at the sender, first off, it will create the layer 7 information, which is the application layer. So if I'm sending an email, that will contain information such as the from and the to field, etc. Then it will encapsulate the layer 7 information in the layer 6 information. Layer 6 is the presentation layer. And then it will encapsulate that in the layer 5 session layer information. Layers 5, 6, and 7 are known as the upper layers, and they're more important for application developers rather than network engineers. Network engineers start to get really interested when we get down to layer 4. So we've got our upper layer traffic composed. That then gets encapsulated with our layer 4 header, which is the transport layer. At layer 4, this is going to be either TCP or UDP, and it will include the port number, such as port 80 if it's web traffic, port 25 for our email example. Now, if you don't already know the details of TCP, UDP, and port numbers, don't worry about it yet. We're going to cover all this information in much greater detail in later lessons and actually throughout the entire course. Okay, next thing that happens is that will then be encapsulated with our layer 3 header. Layer 3 is the network layer. And important information that is included there is the source and destination IP address. A network device that operates at layer 3 is our routers. The next thing that will happen as we compose the packet is the sender will then encapsulate that information in the layer 2 header. Layer 2 is the data link layer. And important information there is the MAC address if we're sending this over an Ethernet network. The network device that works at layer 2 is our switch. And finally, this packet is now ready that we can actually transmit it over the wire. When we do that, we're down to layer 1, which is the physical layer. A network device, which you don't really see anymore, which operated at layer 1 was hubs. So we've now composed the packet at the sender side, we've put it onto the wire, it's going to travel over the network, and it's going to reach our receiver. The order of operations is going to be reversed now, because obviously it comes in at the physical layer. The receiver will process the packet from the bottom layer back up to the top layer now. So it comes in at the physical layer. The receiver will then look at the outside header, which is the layer 2 header, and it will check that this packet is for it. It will check that the destination MAC address in the layer 2 header is its MAC address. If it's not for it, it will just discard the packet. Next up, it will continue with de-encapsulation now. It will then look at the layer 3 header. It will check the destination IP address, and again, it will check that the packet is for it. If not, it will discard the packet. Then we carry on with our de-encapsulation on the receiver. It will look at the layer 4 header. What this is useful for is, imagine the receiver is not just an email server listening on port 25 for email traffic. Let's say it's also a web server as well, listening on port 80 for web traffic. Well, how does it know if this traffic is for its email server application or its web server application? It can tell by looking at the port number. Next, we'll carry on with the de-encapsulation. We'll strip off the layer 4 header. We'll look at the layer 5 header at the session layer. We'll carry on up. We'll then look at the layer 6 header and then the layer 7 header. So that's the whole thing. That's how we got traffic from the sender to the receiver as far as the OSI model is concerned. At the sender side, again, we start off at the top layer. We work our way down to the physical layer. It goes across the physical layer. It will hit the receiver there, and it will then de-encapsulate going in the opposite direction, going from the bottom layer up to the top layer. Looking at the benefits we get from the OSI model, engineers don't need to design a technology to work end-to-end from top to bottom of the model. They can just focus on their layer of expertise and make sure that they comply with the standards for the layers above and below. This leads to open standards and multi-vendor interoperability. For example, if you're an application developer, you can just focus on the top 3 layers. The lower layers are the domain of network engineers, so you don't need to understand them. You just need to make sure that where you interface between layer 5 and layer 4, you're complying with the standards there. Troubleshooting is also easier because you can analyze a problem in a logical fashion layer by layer. It's difficult to overstate just how important the OSI model is to computer networking. As you become more experienced with networking, you'll think according to the OSI model when you're troubleshooting or learning a new network technology. This will be natural for you. This is what I do really every day on a day-to-day basis. And on the job, you'll hear technologies and problems being described according to their OSI layer. For example, if you're troubleshooting a problem and you start looking at it in an overly complicated way, it might turn out that it was just because the cable was unplugged. And you would say to the guy next to you, oh yeah, it was a layer 1 problem. You might also hear of a layer 8 problem. That's when a user has made a mistake. Okay, this is going to be tested heavily on the exam, and like I just said in the last slide, it's really important anyway, not just for exam purposes. For your whole understanding of networking, you really need to know the OSI model. It's going to help you. So we are going to have acronyms that are going to help us remember what the actual names of the different layers are. The classic acronym that you'll see in all the books going back years and years is please do not throw sausage pizza away. So again, the layers were the physical layer, then the data link, then the network, then the transport, the session, the presentation, and the application layer. When you're first beginning, in fact, to be honest with you, I still remember it from the acronym, and it's just automatic for me. I know it's please do not throw sausage pizza away, and that helps me easily remember what the names of the different layers are and what order they come in. Other acronyms you can use if you don't like that one that's relevant to networking is please don't need those stupid packets anyway. Another one that would be relevant to us here is please do not teach students pointless acronyms. And a useful one, please do not take salespeople's advice. If you've been working in networking for any time already, you'll know that's great advice. And my personal favorite, please do not touch Superman's private area. Okay, I think enough said about that. In this lesson, you'll learn about the TCP/IP suite. TCP/IP was developed way back in the 1960s by the US Department of Defense's Advanced Research Projects Agency, that's DARPA. It's a protocol stack which consists of multiple protocols, including TCP, which is the Transmission Control Protocol, and IP, which is the Internet Protocol. So it's not a single protocol, it's a protocol stack. What a protocol is, if you think of diplomats, when diplomats from different countries meet each other, there's a certain way that they're expected to behave and to communicate with each other. In computer networking, protocols basically mean the same thing. So if we've got two hosts and they're going to communicate with each other, there's going to be a protocol which is going to control how that communication should behave, how it should work. TCP/IP, it's the main protocol stack used in computer operations today. There used to be other competing protocols way back in the day, like IPX, SPX, and AppleTalk, but they're really dead now. TCP/IP is now ubiquitous. And whereas the OSI reference model is conceptual, the TCP/IP stack is actually used to transfer data in today's production networks. TCP/IP is also layered, but it doesn't use all of the OSI layers, though the layers are equivalent in operation and function. So it does actually use them, but in the documentation, it only lays out 4 different layers. Let's look at those now. So you can see on the slide here over on the left, we've got the OSI model that we covered in the last lesson. So we've got the 7 layers there. Remember, the way to remember, easy way is please do not throw sausage pizza away. So we've got physical, data link, network, transport, session, presentation, and application. Over on the right, we've got the TCP/IP stack. So you can see we've only got 4 different layers there. Up at the top, we've got the application layer, which maps to all 3 of the application, presentation, and session layers in the OSI model. Below that, we've got the transport layer, which is a one-to-one mapping with the transport layer also in the OSI model. Underneath that, we've got the internet layer, which is equivalent to the network layer in the OSI model. And down at the bottom, we've got the network access layer, which maps to the data link layer and the physical layer in the OSI model. Now, you know, I was saying in the last lesson, it's really important to understand the OSI model. The TCP/IP stack, for sure, if you're working in networking, you're going to know the different protocols like TCP and IP like the back of your hand. But when we're talking to other network engineers, it's more commonly the OSI model that we're going to be referencing. Moving on, looking at some host communications terminology. So when 2 hosts talk to each other, they're going to be exchanging PDUs, protocol data unit. So the PDU is the entire communication all the way from layer 7 down to layer 1 of the OSI stack. We can also divide that into different terms depending on which layer of the TCP IP suite we're talking about. For communications up at the application layer, that's called data. For communications between the transport layer on two different hosts, that's called segments. Between the internet layer, those are our packets, and down at the network access layer, those are our frames. So, just on the last slide, I was saying typically real world, we're not going to be discussing the TCP IP stack like this about the 4 layers. More commonly, we'll use the OSI 7 layers, but on this slide, the terminology actually is commonly used. So if I'm talking about layer 2 communications, I'll call that a frame. If I'm talking about layer 3, I'll call it a packet. And if I'm talking about layer 4, I will call it a segment. Another thing I need to tell you here is that packet officially is at layer 3, but you might have heard me talking earlier on in this section and calling the communication between two hosts a packet. So really the correct term is a PDU, but in day-to-day conversation, often we'll just call communications between two hosts a packet, meaning the entire stack. In this lecture, you'll learn about the upper layers of the OSI model. That's the upper 3 layers, 5, 6, and 7. Network engineers don't typically work directly with those upper 3 layers of the OSI model. They're more relevant to application developers, but we still need to know what they do. And for the exam, we need to know the definitions of each of the layers as well. It's quite likely that you'll be tested on that. So in this lecture, that's primarily what I'm going to be doing, is giving you the Cisco definitions so you'll be ready for the exam. Information included in the upper layers would include the message body and the subject line in an email message, for example. So let's look at the 3 top layers, starting with layer 7, the application layer. This provides network services to the applications of the end user. It differs from the other layers in that it does not provide services to any other OSI layer. The application layer establishes the availability of intended communication partners. Intended communication partners would be the host that this host is communicating with. If you remember from the lecture before when we were discussing the OSI model, you saw that straight line between two hosts at the same layer of the OSI stack. Okay, so the application layer establishes the availability of intended communication partners. That's that straight line going to the other host. It then synchronizes and establishes agreement on procedures for error recovery and control of data integrity. Data integrity means checking that data has not been altered or corrupted in transit. The next layer is layer 6, the presentation layer. This ensures that the information that is sent at the application layer of one system is readable by the application layer of another system. The presentation layer can translate among multiple data formats using a common format. For example, it might need to do this for computers with different encoding schemes. And the last layer of our upper layers is layer 5, the session layer. This establishes, manages, and terminates sessions between two communicating hosts. The session layer also synchronizes dialogue between the presentation layer of the two hosts and manages their data exchange. For example, we might have web servers which have got many users that are using that web server. So in that case, we would have multiple incoming sessions. The session layer keeps track of all of those. It also offers efficient data transfer, class of service, which is similar to efficient data transfer, and exception reporting of upper layer problems. Okay, so that's the definitions of the upper layers. We'll go into the definitions of the bottom 4 layers in the next lecture. In this lecture, you'll learn about the bottom 4 OSI layers. Where network engineers are not typically very concerned with the top 3 layers, we are very concerned with the bottom 4 layers. This is really bread and butter stuff for us. Each of these bottom 4 layers are so important that they're going to have their own dedicated section later on in the course. Here I'm going to focus on giving you the definitions which you're going to need to know for the exam. So the first of the bottom 4 layers, we'll start with layer 4, which is the transport layer. The main characteristics of this layer are whether TCP or UDP transport is going to be used and the port number. Now, if you don't know anything about TCP or UDP or port numbers already, don't worry about it too much for now, because we're going to be covering this in the dedicated section for layer 4 later. For now, you just need to know that if we want the communication between the two hosts to be reliable, then we'll use TCP. If speed is more important than reliability, like for voice or video traffic, then we'll use UDP instead. The other main characteristic at this layer is the port number. For example, port number 80 for HTTP web traffic, port number 25 for SMTP email. Now, there is quite a lot of other information also in the layer 4 header, but we'll talk about that when we get to that particular section in the course. The definition for layer 4, the transport layer defines services to segment, transfer, and reassemble the data for individual communications between the end devices. It breaks down large files into smaller segments that are less likely to incur transmission problems. The next layer is layer 3, the network layer. The most important information at the network layer is the source and destination IP address. Again, there's a lot of other information also carried in the layer 3 header, but we'll talk about that when we get to the later section. Routers are layer 3 devices. They operate at layer 3 of the OSI model. And the definition of the network layer, it provides connectivity and path selection between two host systems that may be located on geographically separated networks. The network layer is the layer that manages the connectivity of hosts by providing logical addressing. IP addressing is our logical addressing. Next layer is layer 2, the data link layer. The most important information here is the source and destination layer 2 address. Again, just like with layer 3 and 4, there is other information also included in the layer 2 header. For example, the source and destination MAC address if Ethernet is the layer 2 technology. Different layer 2 technologies use different formats for their addressing. For example, old legacy frame relay uses DLCI or DULCI numbers for the addressing. With Ethernet, which is what is always used on our local area networks, it's the MAC address that is used here. And switches operate at layer 2. Our switches are layer 2 aware devices. The definition for the data link layer, it defines how data is formatted for transmission and how access to the physical media is controlled. It also typically includes error detection and correction to ensure a reliable delivery of the data. And finally, we have layer 1, the physical layer. This concerns literally the physical components of the network, for example, the actual physical cables being used. Definition of the physical layer, it enables bit transmission, the ones and O's, between end devices. It defines specifications needed for activating, maintaining, and deactivating the physical link between end devices. For example, voltage levels, physical data rates, maximum transmission distances, and physical connectors, etc. Okay, so there you have it. That was the quick overview and mainly the definition of the bottom 4 layers. As we go through the rest of the course, we'll be covering those in much more detail.